Covalent bonding, intro to the bonding model. In metallic bonding model, metals are considered to have lattice structure, where positively charged metal ions are surrounded by a sea of delocalized valence electrons. The valence electrons are free to move throughout the lattice. The sea of electrons, attracted to the cations but free moving, explains many of metals' properties, such as being reflective of light, conductive of heat and electricity, and with relatively high melting point. However, it does leave out many exceptions, such as mercury being liquid at room temperature. In ionic bonding model, ions of different charges alternate in an ionic lattice. The electrostatic attraction is strong, and therefore ionic compounds are mostly solid at room temperature with high melting points. They are brittle because of the lattice shift due to external forces, then the repulsion between ions of the same charge will push apart the layers. The ions are locked in at a solid state, and therefore ionic compounds don't conduct electricity in solid state. However, in molten or dissolved state, ions are free from the lattice, and as a result, ionic compounds become conductive. In this session, we will introduce another bonding type where electrons are shared between non-metal elements, covalent bond. Each bond consists of shared pair or pairs of electrons. Sometimes atoms can share more than one pair of electrons, forming double bond, triple bond. Sharing may or may not be even due to different electronegativity, and therefore some bonds are polar, and we will unpack each of the points as we go. Here is how we can visualize the formation of covalent bond in the example of a single covalent bond forming between two hydrogen atoms. So as the atoms gets closer and closer together, each of the nucleus starts to electrostatically attract the other atom's electron. The covalent bond starts to form, and energy is therefore released. However, once it approaches a equilibrium point and the two atoms become too close, then there would be considerable repulsion between the nuclei of both atoms, and the potential energy of the entire system would rise. So, the covalent bond in the hydrogen molecule represents a position of equilibrium, or balance, or sweet spot, in which the forces of attraction between the nuclei and the bonding electrons exactly match the repulsive forces between the two nuclei. The distance between the two bonded hydrogen nuclei is therefore noted as bond length. Okay, so bond length is the distance between two nuclei for covalent bonds, and the energy per mole required to separate the atoms in the bond is therefore known as the bond dissociation enthalpy. Here we'll show you different examples of covalent bonds. They are all formed out of the tendency of atoms to form a stable arrangement of 8 electrons in their outer shell. That being said, we must know that the octet rule, which is the tendency for atoms to form a stable arrangement of 8 electrons in their outer shell, it would better be considered as a guideline only, as there are a lot of exceptions. For example, hydrogen atom will only need 2 electrons in its outer shell to form a stable arrangement. The transition metals, radicals, don't really follow the octet rule, and atoms that form sometimes they will form incomplete or expanded octet that we will talk about later. Okay. So, example of single bond, as you can see that notable examples of single covalent bonds we can find from group 17 elements, as they all need one more electrons in their outer shell. So they share to achieve a perfect 8. One group over, we go to group 16, where atoms tend to need 2 more electrons in their outer shell. Therefore, they form one double bond. As we know that one double bond is not 2 bonds, it's just one type of bond, that's double bond. And one double bond involves 4 bonding electrons. Similarly, group 15 elements can be predicted to have triple bonds. 3 pairs of electrons share between them in order to achieve a perfect 8. The other electrons in the outer shell that are not bonding, we call them lone pairs. Okay. Now, out of all of these different bonds, every covalent bond is characterized by 2 values: bond length and bond enthalpy. Here are some data in comparison. As we can see that even between the same atoms, single bonds tend to be longer and weaker with lower bond enthalpy, while multi-bonds are shorter than single bonds, but they are stronger than single bonds. However, we'll also notice by the value that double bond does not necessarily double in bond enthalpy compared to single bond. Neither does triple bond triple in energy. The qualitative reason for such observation can be easily explained by what we know from the atomic models. As atomic radius increases, we would expect the atoms to form molecules with longer bonds. As a result, the shared electron pair is further from the pole of the nuclei in the larger molecules, and so the bond would be expected to be weaker. Multiple bonds have a greater number of shared electrons, and so have a stronger force of electrostatic attraction between the bonded nuclei. This means there is a greater pulling power on the nuclei, bringing them closer together, resulting in bonds that are shorter and stronger than single bonds.